Hi everyone, my name is Felipe Gonzalez and I am a postdoc at the University of California, Berkeley. And today I'm going to be talking about how we use computer simulations in order to predict the properties of matter at extreme pressures and temperatures. And to motivate our work, I want you to consider that magnesium, silicon, and oxygen depicted in this box of interacting atoms here are among the three most abundant chemical elements in the universe. And they are very important in planetary science because they form building blocks of planetary formations such as MgSiO3 and magnesium oxide. And in order to understand planetary formation and evolution where extreme pressures and temperatures are achieved, it is important to understand how the properties of matter change with pressure and temperature because they remain largely unknown in this regime and they are mostly driven by quantum effects that have to be taken into account accurately. And I would like to start with this diagram where you can see warm dense matter here in this region of temperatures and densities. You can see lightning discharges at low density and low temperature, the conditions for white dwarf cores at really high densities and high temperatures, and finally the conditions needed for ignition in inertial confinement fusion, which occur at really, really high temperatures. So in order to understand all these phenomena, it is necessary to develop equations of state that are accurate and that span across a wide range of temperatures and densities. So we can study exoplanetary interiors, stars, and predict what will happen with materials in inertial confinement fusion. So I will tell you about the equations of state that we have generated for pure magnesium, magnesium oxide, and MgSiO3. I will tell you about pressure and temperature ionization in these materials and the electronic properties, thermodynamic properties, and we'll end talking about linear mixing. I would like to highlight that the equations of state that we have generated are all available as supplementary material in the papers that I will cite throughout this presentation. So the way in which our approach works is the following. We combine two different simulation techniques, density functional theory, molecular dynamics, and path integral Monte Carlo. So on one hand, DFT molecular dynamics treats the electrons as waves and solves the quantum mechanical problem, finding the electronic structure, and move the nuclei using the Newton's equations of motion. On the other hand, path integral Monte Carlo treats the electrons as paths using the Feynman formulation of quantum mechanics, so they are completely independent. And we use both to create a single equation of state for each of the materials we analyze. And to illustrate how our approach works, I will start describing magnesium, which we recently published in Physics of Plasmas. And the way it works is the following. We perform a series of simulations. Each of the points you see in this diagram is a simulation at a given temperature and density. And the simulations that are performed at highest temperatures are done with PIMC. The simulations below 1 million Kelvin are done with DFT molecular dynamics. And at each of these points, for each of these simulations, we can calculate pressure and energy and monitor them, for example, along an isochord at a given density. And this is what you see here in the diagram on the right. So the temperature is increasing to the right. And you can see that the pressures and energies that we predict with DFT molecular dynamics are consistent with those that we predict with path integral Monte Carlo in this overlap region. And it does so for each of the isochords we simulated. So we can generate, therefore, an equation of state that is consistent and spans from temperatures of 20,000 Kelvin up to almost 1 billion Kelvin. We can also monitor the properties of the fluid as temperature increases. And you can see here in this point at very high density and 20,000 Kelvin that it's actually a frozen sample. So this is an amorphous that has a structure here, but all the rest of the simulations at lower densities and other temperatures are liquids. And you can see that the liquid very quickly loses its structure as the temperature is increased. We also studied pressure ionization, and the way we do that is the following. Along each of the isotherms we explored at constant temperature, we monitored the energy of the system, the total energy, and what we see is that the energy attains a minimum. And uh, the reason that the energy increases after this minimum is due to quantum confinement effects. So we believe that this is a good criteria to distinguish pressure ionization from temperature ionization, which are depicted in different colors in the diagram on the left. So we use this energy criteria to distinguish where pressure ionization starts, which is described by this black line in the diagram. We also studied the shock Hugoniot curve of magnesium, which is the red curve that you see here on the right. And the way in which we obtained it is the following. In our simulations, the energy and pressure are functions of the volume and temperature we choose. So we can build this function h, which will be a function of volume along an isotherm. So we just have to find out where this function crosses zero along the isotherm, which is basically the shock Hugoniot condition. Doing so for all isotherms allows us to obtain the entire shock Hugoniot curve. And you can see here that there's a maximum on the bottom, which corresponds to the excitations of the L shell electrons of magnesium, while the maximum above correspond to excitations of the K shell electrons of magnesium. You can see that radiation effects are only important for pressures that are above 300,000 GPa, while relativistic effects only take place at pressures that are beyond 2 million GPa. We also studied the effects of precompression and preheating, which basically deform a bit the shock Hugoniot curve that starts from ambient conditions. We also studied the electronic structure of magnesium, and we do so studying the electronic density of states, where you can see here that there's a peak, a large peak attributed to the 2p states, while this small peak here is attributed to the 2s states. There's a band gap there that closes upon compression, as you can see in the diagrams below. However, the band gap between the 2p states and the conduction band here on the right never closes for the conditions we explored in this study. The smearing, however, that is around the Fermi energy depicted as vertical bars here is very large, so the material still remains as a conductor. In the diagram on the right, you can see the number of the electrons in the conduction band, which is 2 electrons per atom at low temperatures. And you can see that it's clearly something interesting happening here, around 250,000 Kelvin. This number is larger than 2, so we can say that at 250,000 Kelvin, the electrons from the L shell start being ionized by temperature. And you can see that this ionization decreases upon compression. Finally, we studied the K-shell ionization of magnesium, and we do so with the nucleus electron pair correlation function. And the way we do it is the following. Here in dashed black line, you can see the reference for an isolated magnesium atom, which at about 0.2 Bohr radii has already enclosed 2 electrons. But in the magnesium plasma, we have more electrons around, so this function increases with radius. And you can see here that at 1.3 million Kelvin, this function is below 2, which means that the ionization of the K-shell electrons, the innermost electrons, has started. So we need temperatures above 1.3 million Kelvin in order to ionize the K-shell of magnesium atoms. We also studied magnesium oxide, and we proceed in the same way. We do DFT simulations, PIMC simulations, and we obtain the shock Hugoniot curve. But in this case, we did have access to experimental data, and you can see that the agreement between the black curve, our prediction, and the experiments is quite remarkable. There are 2 experiments available, and the the agreement between our predictions and experiments is very good. We also studied the density of state of magnesium oxide, where now including oxygen in the system generates this peak here that basically generates a high hybridization of the L shells of magnesium and oxygen, which are become gradually ionized by temperature. This effect becomes even more evident at higher densities. Finally, we studied MgSiO3, which is a work we presented last year at the AGU as preliminary work, now it's published. And we proceed in the same way. We do PIMC at high temperatures, DFT-MD at low temperatures. We calculate the shock Hugoniot curve. And we confirm that our equation of state is consistent in this overlapping region between the two methods. And we also have access to experiments in this case. And once again, the agreement between our predicted shock Hugoniot curve and experimental data is quite remarkable. We have very good agreement here. And we also separate the regime of thermal ionization from pressure ionization using our energy criteria. And in this case, we studied also the heat capacity, which is quite interesting because as you can see here, the specific heat increases with temperature, but there's a maximum here. This maximum here corresponds to the ionization of the K-shell electrons of the oxygen atoms, while the second maximum here corresponds to the ionization of the K-shell electrons of the magnesium and silicon atoms. At even higher temperatures, we recover the ideal gas limit where the specific heat is just 3/2 the Boltzmann constant. We also studied the radial distribution function of MgSiO3, and you can see here that the three species start losing their structure in the liquid as temperature is decreased. And this allows us to understand how the atoms bond in this material. Finally, we study the ionization of the K-shell electrons in MgSiO3, where we can see the ionization of the oxygen atoms already starts at 1 million Kelvin in this material. So I would like to finish by talking about linear mixing, which is a study that is motivated by the fact that we have access to each of the individual equations of state for magnesium, silicon, and oxygen. So we want to try to see whether we can do a linear combination of the equations of state and predict what the properties of the mixture will be. And this is what we do. We do so at constant temperature and pressure, and we predict under the linear mixing approximation what the energy and the volume will be in the mixture. And doing so, we rederive the shock Hugoniot curve, which you can see here in this diagram. You can see that the original shock Hugoniot curve for MgO in blue is in remarkable agreement with the approximation of linear mixing. We can reproduce the maximum compression peak and all the features here in this high pressure, high temperature region. And the approach works really well for temperatures above 100,000 Kelvin. We can see nonlinear effects taking place here where chemical bonds become more important. So in the case of MgSiO3, we also have a remarkable agreement between linear mixture and the original shock Hugoniot curve that reproduces the features here, the maximum compression ratio. And in this case, it works even a little bit below 100,000 Kelvin. So I would like to finish showing you the comparison of the three materials we have analyzed today, MgO, MgSiO3, and pure magnesium. And you can see that the shock Hugoniot curve of both MgO and MgSiO3 are very, very similar. And you can see that the peak here that is aligned corresponds to the K-shell ionization of the magnesium atoms, while this feature here corresponds to the ionization of the K-shell electrons of oxygen atoms. So we have produced a consistent and available equation of state that spans across a wide range of temperatures and densities that you can download. We have found maximum compression ratios of 4.9 and 4.7 for the shock Hugoniot curves of these materials. We studied the K and L shell ionization, and we have demonstrated that linear mixing works really well for temperatures above 100,000 Kelvin. And with that, I will just like to acknowledge my funding sources and thank you for your attention.